Alrighty, in this section, we're going to look at Hess's law and how we can use it in conjunction with Lewis dot structures. Remember, Hess's law is just a path-independent approach to calculating the enthalpy of a reaction. So it doesn't matter what approach we take, we're all going to get the same value or close to the same value at the end of the day. We're going to use Lewis dot structures because then we can analyze bond breaking and bond formation to calculate that enthalpy. First question I want to ask you all, does breaking a bond take energy or release energy? So jot down your answer real quick, take a second to think about it. Alright, so typically when I ask this of a group of students, most students will tell me that bond breaking releases energy. Unfortunately, that's not correct. And I know that misconception comes from a lot of different ideas, but here's what you need to think about and have stuck in your head. If I want to break this stick, did that take energy or release energy? And I think most of us would agree, trying to break a piece of wood or breaking a stick, in lecture I'll go ahead and break a pencil. Breaking something, including a bond, takes energy. It's an endothermic process. On the flip side, if you form a new bond, that's when you release energy. The values in the table, they represent the energy required to break certain kinds of bonds. So they're all positive. This means that we're talking about endothermic processes. Breaking bonds is endothermic. And they're all associated with breaking bonds. If you can remember this relationship, you won't even need the formula that's listed below. If you can just remember that breaking bonds requires energy, then all the pieces will fall together. And we'll see that in the examples. So in this first example, we're asked to determine how much heat is released when we combust methane, CH4. So the first step would be to come up with a balanced equation for the combustion of methane. So the combustion of a hydrocarbon requires oxygen gas. And we know, it's very systematic, we know that it's going to produce carbon dioxide and water. Let's balance it. We have 1 carbon on both sides, 4 hydrogens. So now if I put a 2 out front, I have 4 hydrogens. 2 oxygens and 2 oxygens for a total of 4 oxygens. So I'll put a 2 out there and I have 4 oxygens. All right, so now that it's balanced, now that we have a balanced equation, the next step, because we're analyzing bond breaking and bond forming, we need to draw Lewis dot structures for all of the molecules or species involved. So I'll start with methane, and you know I like to do my electron math. So carbon has 4, and then we have 4 hydrogens, so that's another 4. And it's been a while since we did this. Remember, these are the number of valence electrons. So carbon's in group 4, so that's why we have a 4. Hydrogen's in group 1, 1 times 4 is 4. So there's 8 valence electrons available to build my methane. So the bonds count twice. They consist of 2 electrons. So I have 2, 4, 6, 8. The octet on carbon is satisfied, and hydrogen can only do a single bond. So that's good for methane. For my oxygen gas, oxygen's in group 6, so I have a total of 12 electrons to build that structure. You might take a little bit of time to work it out. I know just from experience that oxygen has a double bond. And then we have 2, 4, 6, 8, 10, 12. And we have octets on both oxygens, and we used exactly 12 electrons. carbon dioxide. So we have 4 and then 2 times 6 for the oxygen. So 12 plus 4, that's 16 electrons for our carbon dioxide. Carbon's the central atom because it's less electronegative. And again, I know it's not entirely fair, but I do know from experience that carbon dioxide has 2 double bonds. And then I want to satisfy the octet. So I'll do 2, 4, 6, 8, 10, 12, 14, 16. And then the last one we'll do is water. Water has a total of 8 valence electrons. So we have a water molecule. The other thing that you're going to want to capture when you're drawing out your Lewis-Dot structures are the coefficients. So when I do a Hess's law problem like this, I always put my coefficients out front too. And you'll see why in just a second. So now we want to analyze the heat associated with every single bond. So we're looking at breaking all of these bonds. So we're going to expect positive values on this side. So this entire side is positive because we're going to break all these bonds. For methane, we need to break 4 carbon-hydrogen bonds. And we analyze, the values are for individual bonds, right, between 2 things. So we want to count each individual bond. For oxygen, we have 1 double bond. Double bonds have different values than single bonds or triple bonds. We have 1 double bond between the 2 oxygens. However, there's 2 oxygen molecules, so I'm going to do 2 double bonded oxygens. So this is everything that's happening on the reactant side. And we want to add up everything that's happening on this side, but because it releases energy, I'm going to put a negative sign right there. But I'm going to put that negative sign and not worry about it until I'm done with the problem. So another big parentheses. On my carbon dioxide, I have a carbon-oxygen double bond, 2 of them. And then if I just had 1 water, I would have 2 oxygen-hydrogen single bonds. But because there's 2 waters, now I have 4 oxygen-hydrogen single bonds. Alright, so once we've broken it down in terms of the types of bonds, then we can go to our table and start looking up numbers. So for carbon-hydrogen, I'll do 4 times 410 plus 2 times, and then oxygen double bond is listed at the bottom, it's 498. And 2 times 732 plus 4 times 460. So I add up everything that's going on with the reactants, and when I did that, I got 2,636 kilojoules. I add up everything that's going on with the products. When I did that, I got 3,304 kilojoules. This is a positive value because it takes energy to break bonds. This second term is a negative value because energy is released when bonds are formed. And it's the difference between the two that determines whether the overall reaction is endothermic or exothermic. So when we subtract these, we get negative 668 kilojoules. which is going to be our heat of the reaction. And this makes sense. It's negative, it's exothermic, and that's what we would expect from a combustion reaction. If it was positive in combustion, then I would go back and definitely check your work, because we wouldn't expect an endothermic combustion reaction. Alright, so here we're asked to analyze and calculate the enthalpy of the reaction for the combustion of a rocket fuel, hydrazine. This time they gave us a balanced equation. And so we'll jump in at the point of drawing out our Lewis-Dot structures. So 2 nitrogens, they're in group 5, so we have a total of 10 valence electrons for the 2 nitrogens. And then 4 hydrogens, each one of them brings 1 valence electron. So we have 14 electrons. And so we're going to get something that looks like this. So 2, 4, 6, 8, 10, 12, 14. And then if we look at each nitrogen, it has 8, 2, 4, 6, 8 around it, so the octet rule is satisfied. Oxygen gas, we did that in the previous problem. Two nitrogens, so we're looking at 10 electrons. So nitrogen gas actually forms a triple bond. So 2, 4, 6, 8, 10. And then water. All right, so after this, we want to analyze the number and type of each bond. Here we have hydrogen connected to nitrogen, and that appears 4 times. So I'm going to do 4 of these hydrogen, nitrogen. The order doesn't matter. I could have done nitrogen, hydrogen, however they have it listed, but 4 of those bonds. And then in the middle, I have 1 nitrogen-nitrogen bond. And then with the oxygen, I have 1 oxygen-oxygen double bond. So that's everything that's going on the reactant side. And then I'm going to subtract. And then I have 1 nitrogen-nitrogen triple bond. And with the water, again, individually, I would say, oh, I have 2 oxygen-hydrogen bonds. But because there's a coefficient out front, I need to multiply all that by 2. So at the end of the day, I have 4 oxygen-hydrogen single bonds. Okay, and then we're going to look up all the values in the table. So I'm looking at 4 times 390 plus 1 times 240 plus 1 times 498. The nitrogen-nitrogen triple bond is 900. It takes 945 kilojoules of energy to break that bond. And then I'll do 4 times 460 for the water. Getting back to this for just a second here. The nitrogen-nitrogen single bond comes in at 240 kilojoules. But the triple bond is 945 kilojoules. And you're going to notice similar patterns for series where you're moving from single to double to triple. The more bonds, the more effort or energy it takes to break that bond. And it makes sense. If I had grabbed a bigger stick, it would take more energy for me to break that bigger stick. So expect higher values in a series, higher values for the double and triple bonds compared to the single bonds. So we want to add up all of this. And when I did that, I got 2,298 kilojoules. Positive takes energy. Negative, the formation of the bonds releases energy. So 2,785 kilojoules. I subtracted those values and I got a delta H, an enthalpy for my hydrazine combustion reaction of negative 487 kilojoules. Again, combustion, we would expect it to be exothermic.